Today we're going to start discussing the area of physics called kinematics. These are the two kinematics equations that we're going to use. Basically, kinematics is the study of problems involving projectiles, things undergoing constant acceleration. And these two equations pertain whenever we have a constant acceleration, which is going to be an extremely common problem for us. Okay, this first one tells us the velocity at any time t is equal to whatever our initial velocity is plus at, plus the change in velocity caused by acceleration. So this is our initial velocity, v0, v at time 0. Sometimes people will call that v naught. And this is the change in velocity caused by acceleration. On the other side, we have our position formula. Our position at time t is equal to whatever our starting position was plus whatever v naught t plus whatever our position would be based upon the existing velocity plus 1/2 at squared. That would be whatever our velocity would be as a result of the accelerations also. So those are the two kinematics formulas, and we're gonna spend quite a bit of time with them, but they provide the velocity and position of an object undergoing a constant acceleration. Now remember, acceleration is a constant, and that constant may be 0. That's going to become an issue. I'm going to simply throw it out there as a point right now, but let's pay attention to it. Okay, so these formulas, if I just do a little bit of massaging, I could say velocity at time t minus velocity initial equals at. This is simply the change in my velocity is equal to acceleration times time. That's all we really need to think about. In this one, I could take this and say my position at time t minus my position initial, that's my change in position, is equal to whatever I would have changed had I not had any acceleration, plus whatever I changed due to my acceleration. These equations are going to break down fairly simple, but let's just plug in something and get an idea where they go very quickly. Let's assume we have a drag racer and he is accelerating at a constant speed of, let's just say, 4 meters per second squared. It's a drag racer in a race. So he starts at point 0, he starts at the beginning, and his initial velocity is also equal to 0. X is 0, and velocity initial is 0. So this drag racer, we want to figure out where, if this drag racer had a constant acceleration, where would he be in 5 seconds? Well, let's just go through very simply how we set up these equations. Our velocity in 5 seconds is equal to our initial velocity, which was 0, plus our acceleration, which we gave as 4 meters per second squared, times the time, which was 5 seconds. And that's equal to 20 meters per second. That will be his speed in 5 seconds. Now let's look at how far he's gone in 5 seconds. X at time t, x at 5 seconds is equal to 0 plus my initial velocity, which was 0 times 5, plus 1/2 4 times 5 squared, which means his x at time 5 is going to equal 50 meters. That's all there is to using these equations. And we will spend a lot of time dealing with them and dealing with frames of reference and everything else. And that's going to add a little more complexity, because what if he started backing up? What if he was doing all sorts of things when he did start with a velocity? But that's your basic equation. But let's look at them a little bit more detailed mathematically. So let's just take a look at the units first. In order for these equations to work, each segment has to have the same units. We know that from our basic algebra. Well, the units for velocity are meters per second. That's our velocity at time t. And our velocity initially is also meters per second. The units for acceleration are meters per second squared, and the units for time are seconds. So that's going to cancel out, and that becomes meters per second also. So that works. Let's look at the position formula. The position is going to be so many meters away. How far did he get? Meters equals meters. Velocity is in meters per second. Meters per second. Time is in seconds times seconds. So those cancel out. Give us lots of money. That cancels out and gives me meters also. And acceleration is meters per second squared. Time is in seconds, and I have that time squared. So the second squareds cancel out, and I end up with meters, 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 meters. So it does work. It's important to think of that. Sometimes people get confused. Let's just look at the general format of these equations. T squared, t to the first power, t to the 0 power. This has seconds squared, seconds, no time at all. So the value, the exponent on t is the same as the exponent on the seconds in the other unit. So meters per second squared, that tells me the time has to be squared. But it is t to the second, t to the first, t to the 0. T to the first, t to the 0. That format will occur often. Now let's look at where these equations actually come from. Because I told you in the beginning of this whole course that everything is just a function of F equals ma. And these, surprisingly, do come straight from F equals ma. In order to get those two kinematics equations from F equals ma, we're going to need to resort to a little calculus. Many of the students in this class are taking calculus, took it last year. I don't care if you're taking honors, AP, or whatever. The basics are here. Let's take a look at that. If you're not taking calculus, you're just going to have to hold on, and you're getting prepared for some math you see coming down the future. So if I have F equals ma, I could turn that around and say acceleration equals F over m. And as long as F and m both remain constant, I will have a constant acceleration. That's a common scenario often. There's a lot of things that can change that. I might have a variation in force. An engine, as I'm turning, might develop a little more force as it gets up to speed. And when it gets where it's winding out the top end, it may find it drops off. So cars don't have usually a very linear acceleration for more than a very short stretch. A rocket may go the other way. They have a constant thrust, but as they're burning fuel, their mass decreases. Then, when they go to the second stage of the rocket, they have a huge mass decrease, a gigantic change in force because they now have a different thrust or a different engine driving them, and then a continual mass decrease. So we might see in real situations either the mass or the force vary. But for now, we're just going to look at situations where they stay the same. And a good example of something staying the same is if I drop a bowling ball. The mass of the bowling ball will remain the same all the way down, and the force on that bowling ball, as long as it's in a vacuum or in a relatively slow speeds, which means like a third-story building, wind resistance will be relatively negligible, and so the force will be mg, the mass times the gravitational constant. So that will also be constant, and those will all accelerate at the same time. So that's our initial one. A is equal to constant. Now, in calculus, we have something called an integral. It's the area under a curve. And if you are aware of calculus, follow me. If I take the integral of a constant, the integral of a, with respect to t, I'm going to get some new units. I'll call it z equals at plus a constant. This was my constant acceleration, a. The units of this new thing are going to be meters per second squared times seconds. So they're going to be meters per second. Thus, the integral of acceleration is velocity. If this is velocity, I can then change this and say this is velocity at time t. And I can say that this, c1, was my velocity at time 0. You'll notice that's my position formula we just had before. I mean my velocity formula. We had velocity at time t is equal, and we had it in reverse order. v0 plus at. That's a common way to see the formula. You'll see them often written both ways. The first one, the way we showed them initially, because that has a physical context meaning, and physicists tend to often write them that way. This one, because it's derived from the mathematics, has a more of a mathematical meaning, and so mathematicians will more often write them this way. Get used to seeing them written both ways. I'll do both ways in class. If we take the integral of velocity, we're going to get some new thing, and that's going to equal 1/2 at squared plus v0t plus some new constant. Now, let's look at the units here. Acceleration is meters per second squared. Time is seconds, so that's second squared. The units of this are meters. Meters per second times second. These are meters. So, if these are meters, this must therefore be our x final, and this must have been our x initial. We now have both of these equations that we have used, that we're going to be using, this and this, the two kinematics formulas, both derived from calculus, but they both come straight from F equals ma. They're mathematically just a derivation or just an integration of F equals ma. So let's take a look at that bowling ball we were going to drop before. Let's say it has a mass of 5 kilograms, which is about 11 pounds. It's a rather light bowling ball. Okay, we're going to drop this bowling ball. As I hold it up in the air, there is a force of gravity pulling down on it equal to mg equal to 5 times 9.8, or 49 newtons. If I'm holding it, there must also be a force of 49 newtons. That's the force of me holding it up. And so that object is going to stay there in my hand. If I let it go, if I remove this top force, it's going to start to accelerate down now due to gravity. If I increase the force, I could actually accelerate it and throw the ball up in the air. For now, let's just assume I drop it. I let this go. Now, if we go to F equals ma, F equals ma, we see the force, which is 49, equals 5 times a. The acceleration equals 9.8 meters per second squared, which is the gravitational constant. So it's always going to turn out that way. The acceleration will be the gravitational constant, no matter what the mass of the object was. Let's take this and put it algebraic. Let's stay in the algebraic realm, and let's say that this has just a mass, m. Then, if we take that, we're going to say the force pulling down is equal to m times the gravitational constant in that planet. Now, In doing algebraic work, we don't usually put in the 9.8 meters per second squared. And the reason is that locks us into units. That locks us into the metric system. As long as I keep this just as g and don't put any units, the new person can come along and say, well, I want to use the English system and I want to use 32.2 feet per second squared. Or you could take it to any other planet and use whatever that gravitational constant is. Not that we're going to planets too often right now, but you get the idea. You can use whatever you want, but as long as I put in g, not 9.8. Okay, so the force acting on this object is mg. F equals ma. The force is mg equals ma. Now let's take a look at that. I put this forces down, and I'm calling down positive, up negative in this range because I have that force acting down. That's an issue we're going to talk about in our next video, which you're going to look at tomorrow night, about that reference system. We flip it all the time. But g itself, the value of g is 9.8. If I want to make it negative, I put a negative in front of it. Or I put a positive in front of it. But the value of g itself is 9.8. Okay, the masses cancel out algebraically, and I get acceleration equals g. Any object of any mass will accelerate at a rate on Earth of 9.8 meters per second squared. Now, with that knowledge, we could calculate how far it's going to fall. A bowling ball, a skydiver, a pencil, a physics book. Not that you would ever throw a physics book out of an airplane or something like that, but maybe an English book. Okay. So, let's see in 10 seconds, if we ignore wind resistance now. Now, of course, we realize that in reality, things don't just continue accelerating unlimited because there is wind resistance. And you've heard of a term called terminal velocity. That is not the speed, well, we'll keep that sick joke out of it. Terminal velocity is the maximum speed something will fall in free fall. For skydivers, that number is somewhere like around 120 miles per hour. And here's what happens. When he first jumps out of the plane, he has a certain mass, and he has a force of mg pulling him down, and that force stays the same. His weight, the force of gravity pulling on him, is constant throughout. The wind resistance, however, varies with his speed. In the very beginning, he has no wind resistance. As he goes faster, the wind resistance gets higher and higher. Thus, the net force gets less and less. Eventually, he will reach a speed where the wind resistance is equal to the weight. At that point, the net force equals 0, and acceleration, therefore, equals 0. He will stop accelerating. Net force of 0 does not mean that his velocity stops. It simply means his acceleration stops. Since his acceleration stops and he has speed, he will continue at the speed he's going. So we're going to ignore that, though. We're going to drop this skydiver off the moon so there is no air to consider ourselves with. And we're just going to see how fast and how far he'll fall in 10 seconds. Drops out of the plane. Regardless of his mass, notice the equations. Velocity at time t equals acceleration times time plus v naught. And position at time t equals 1/2 a t squared plus v naught t plus x naught. Have no mass in the equation. They are simply functions of what that gravitational acceleration is, 9.8, and time. Mass is irrelevant in these problems. And that's a tricky thing. If it's not in the equation, we don't use it. It doesn't matter. So, if I take this and say in 10 seconds, I want to know how far it falls. Let's first just define our reference system. I'm going to go with this, what we've been doing. Down is positive, up is negative, and consequently, my acceleration due to gravity is negative 9.8. I'm sorry, is positive 9.8. It's down. and I'm calling down positive. So my velocity at time t, velocity at t at 10 seconds is equal to 9.8 times 10 plus 0 is equal to 98 meters per second. That's his velocity in 10 seconds. His position in 10 seconds would be x at 10 equals 1/2 a t squared plus v0t plus x0. We're going to say the plane is where he starts, so that goes to 0. His initial velocity vertically was 0, and this is going to give us x at time 10 equals 1/2 9.8 times 10 squared. This is 9.8 times 50, which is equal to 490 meters. That's all there is to these equations. They're not that tricky. However, as we've seen before with F equals ma, how we apply them and what we do with them can be a little bit, require a certain amount of insight and effort from you. So let's move on. We're going to look at a lot of problems over the next week, and let's go from here. These are our initial equations, the kinematics equations.